and stochastic optimal transport.
Okay. Thank you very much for a nice introduction. And first of all, I'd like to thank organizers for giving me the opportunity to give a talk in this meeting. I'd like to
Qu'est-ce qui se passe? Ah bon. Attends,
okay. You hear me, right? Okay, let me start. So okay, the plan of my talk is this, where I first briefly introduce Schrödinger's program, and then Nelson's program, and then stochastic optimal transport. Maybe, okay, since I'm talking in my house, so maybe I should stop video because of internet program. And last program is maybe I cannot talk about last program because I prepared 63 pages. Well, anyway, let me start. Wait a minute. Strange. Oh. Okay. Okay, maybe this is boring for all of you, but let me start from Schrödinger's original program, which I found in the literature. And suppose that we have two sets A and B, where particle, you find particle in each point, and the number of total particle is capital N. Okay, and each particle moves independently to this set B, and transition density from AI to Bj is given here. It's a random, right? Oh, actually, can't see. Okay, and the constraint is this: number of particles in each point are fixed, and he wanted to find the maximum probability of such events. Since each particle are independent, probability is described in this manner. Okay, where Cij is the number of particles that move from point AI to Bj. And constraint is this. In each point, particle move from set A to B, but each point in Bj, the number of particles is fixed. So you can write in this manner. This Ki is a number of particles in AI. Therefore, this is equal to Hort, and then this is equal to Hort. And we suppose that number of particles which move from AI to Bj is sufficiently large. Then using a starting formula, a program, and taking logarithm of the probability, the program becomes a maximization of this guy under this constraint. Setting setting P0, P1 by this equation, and then Qij denote Cij over N, then this maximization program becomes a minimization program. Here, H is a relative entropy of Qij with respect to mu I Pij, right? And making this problem more general, in my talk, I call Schrödinger program by this definition. First of all, I'd like to define the relative entropy of Q with respect to P, where QP are, this is RD times RD. Q and P are probability measure on RD times RD. If Q is absolute, continuous with respect to P, then this is, well, probably you know the definition of relative entropy anyway. Okay, let's define the set of admissible probability measures on RT times RD, which have the first marginal is P0 and the second is P1, right? then Schrödinger's program can be written this way. Minimum of this relative entropy under this constraint. Here, px dy is a probability measure for each x. And right, okay. Oh, sorry. So as a general program, this is a minimization program of relative entropy or probability measure, which satisfies this constraint. So in his paper, he didn't solve this program, but he gave a equation for, he gave an Euler's equation for this program. Well, when I was a graduate student, I learned the name of this equation, the Schrödinger's function equation. Right, so in Japan, this name is popular, but I don't think maybe Schrödinger system is much more popular in Europe. So anyway, it's not me who used this name. I mean, I was just taught. It's okay. Anyway, let me explain this. Euler's equation, okay, taking first variation of this Schrödinger's program, you get this equation. And oh yeah, in my talk, I already assume this P1 has density. Okay, and let's take a probability when P0 P1 and Pxy dy, which is a probability measure on RD, find the product measure nu 0 times nu 1, non-negative sigma finite product measure, which satisfies this. And the minimizer of Schrödinger's program is actually nu 0 dx pxy nu 1 dy. Okay. If we have solution to this equation, then you find the minimizer of this. Oh, by the way, this set AP0 P1 is a compact set. Compact set? Yeah. So this has and relative entropy is lower semi-continuous in Q. Therefore, minimizer always exists, right? If this is bounded, finite. If this guy is finite, okay. So, but this in this equation, you have to find measure, product measure. So let me introduce another description of Schrödinger's function equation. Let's define U0 and V1 by this equation, by this equality. Here, if Pxy is, for example, the Gaussian kernel, U0 is a semi-convex function, so it's V1. But anyway, if we define U0 V1 by this equation, equality, then solution to Schrödinger's program can be written in this manner. Okay, and the Schrödinger's function equation is equivalent to this system of equation for function, right? If this is a solution, and if Pxy is a nice function, then U0 is also nice. I mean, if for example, if P is a Gaussian kernel, then U0 is semi-convex, right? So, and the nice viewpoint of this description is that instead of finding a sigma finite measure, you find a nice function U0 plus V1, right? Singularity of P0 or P1 disappears here. This is a function, but it doesn't mean that you find a nice idea to solve the Schrödinger's function equation. I also introduce another description of Schrödinger function equation. Actually, Schrödinger's function equation is also equivalent to this equation. This is one, it's not system, just one equation. What's V? V star. V star is a convex conjugate of Schrödinger's program. Okay, I just recall the Schrödinger program here. And if you solve this equation, then set nu 0 dx by this equality, then you solve Schrödinger's function equation. later I explain, I refer to references. Now I don't do that. Okay. And next I explain Schrödinger's problem from viewpoint of SDE, stochastic differential equation. For the sake of simplicity, I only consider that Pxy is written by this Gaussian kernel. And let's set H by this equality. So H is a backward harmonic function of T and X, okay? And here's Jameson's result. If P1 has a density, then this function H is has this regularity, and this stochastic differential equation has a weak solution, unique weak solution. Here, WT denotes a Wiener process starting from 0. And the reason Jameson considered this SDE is the following: joint distribution of x0 and x1 is exactly the solution of Schrödinger's problem, which can also be written by this manner. In particular, Schrödinger's problem is equal to this, but by this description, it's also equal to relative entropy of Px with respect to Px0 plus W on the path space. And this is equal to, by Grisha formula, is equal to this one, right? So in the starting point, Schrödinger's problem was a problem on the measure, this variation problem of the measure on Rd times Rd, but it can be written by the relative entropy of measures on the path space. Indeed, the distribution of X can be written this way. So it's absolutely continuous with respect to Brownian motion times plus x0, initial random variable. So, and the following was very actually interested to me when I was a graduate student, that Professor Zambrini's paper result. Well, xt, I mean, which was given, which was called H plus process and constructed by Jameson, is a unique minimizer of this problem. Here, point is this. This is the entropy, relative entropy. So if you only look at the relative entropy, story ends here. But if you, instead of considering this, this description, if you look at this equality, then right-hand side is a, if you put this guy in here, then program becomes a kind of stochastic control program with fixed end-time two endpoint distribution. So this idea, understanding, made me to generalize this program as a program of stochastic control with a more general cost function. Okay. So, right? Okay, anyway. And as a remark, Schrödinger's program can be written in this way. This is nothing but just that I substitute equality. And B is finite. B is finite if P0, P1 has a second moment and differential entropy is finite. Because Schrödinger's program is minimum of this kind of relative entropy where the measure in here have a first and second moment P0 and P1. So if this is, so this is sufficient condition for the finiteness of B, Schrödinger's program. And well, this is equality. So if B is finite, then log H1 minus log H0 is a integral function, right? With respect to this measure, joint distribution, right? But how about each H1 and H0? Is it integrable for in P1, P0? It's not always true. if B is finite and if P0, P1 has second moments, then each function is integrable in PT. HT is integrable in PT, which can be shown by the result in this paper, or you can prove it directly. But anyway, so one, I also want to know, maybe it's known, but I don't know, sufficient and necessary condition so that this is true. So if somebody knows, anybody knows the condition, let me know. Anyway, okay. So next Next I discuss zero noise limit of Schrödinger's program, right? And first I briefly introduce Monge-Kantorovich program with a quadratic cost. It can be written in this manner. Well, it's an infimum of x0 minus x1 square, mean value of x0 minus x1 square, where p distribution of xt is equal to pt for t1, 0 and 1. But by Jensen's inequality, actually this infimum can be written in this way. xt is the absolutely continuous stochastic process. Oh, I'm spending much time. And this infimum equals this guy. So it looks like, this description implies that, well, this is a stochastic control program with no Brownian motion part. So it is true, since when we consider H plus process, terminal distribution should have a density, but I don't want to assume that condition. So we regularize terminal distribution by this. Okay, and instead of Brownian Wiener process, we consider square root W Wiener process, and put epsilon in every notation, like x can be written x epsilon, b can be written x b epsilon. Then in this case, the drift vector is dx log h epsilon times epsilon, right? Oh, I'm not sure. Okay. Then the following is known. If pt has a second moment for t0 and 1, and if p0 has density, then p epsilon converges to Schrödinger's program. In the zero noise limit, it converges to the Monge-Kantorovich program. Besides, drift vector of the H plus process satisfies this condition, where phi is a convex function. Okay, and well, x epsilon 0 is equal to x0. Right? Anyway, and this function actually by this function, this measure is a unique minimizer of Monge-Kantorovich program. So this gives a probabilistic proof, SDE proof to the Monge's program with quadratic cost. So since I proved this, I found some, I felt kind of some possibility to generalize optimal transportation theory in the framework of SDE. So I tried, and also now here in diffusion matrix is constant. In that case, P epsilon is actually martingale. Therefore, this equality implies that this equality here take a supremum over all R of T between 0 and R. This can be proved easily by the Dubs inequality. So, but when diffusion matrix is not the constant matrix, P epsilon is not necessarily martingale. Okay, maybe I should skip. Sorry. Okay, the first part of my talk is from section 7 of this paper, and on Schrödinger's program, this is I don't know how to pronounce this guy's, I refer to this guy's paper and Professor Zambrini's result. And also, I also refer to these guys. I'm sorry, skip. And this paper gave a counterexample that HTX does not belong to L1PT, and this is a generalized limit. Also, on the Schrödinger program, I refer to some nice survey of Professor Leonard, and well, I wouldn't say it's nice, but anyway. Okay, next, Schrödinger's functional equations. Okay, in Bernstein's, he didn't give a proof, but he said he pointed out Schrödinger's functional equation has a solution if pxy kernel function is positive and continuous. Sorry. And this paper, now probably it's famous in data science. This person solved Schrödinger's functional equation by the successive approximation. I would say in one-dimensional case, and it's generalized by Burin the compact Hausdorff when the state space is compact and the Hausdorff topological space. And in this paper, state space is Sigma compact space. Yeah. So it also gives considers case. It includes a case of Euclidean space. And in this result, important assumption is kernel function pxy is positive and continuous. And SD in this paper, he considered SDE for H+ process. And this also gives a different approach, but proof is very difficult for me, so I didn't even read. I mean, I just took a look and found it difficult. And in this paper, I consider the continuity of solution to Schrödinger's equation, Schrödinger's program, continuity in the terminal distribution P0, P1, and kernel function Q. And in this paper, topology was strong topology, and this paper, topology was weak topology. Yeah. Oops, sorry. And the application of Schrödinger's program is probably this algorithm, synchron algorithm. But I don't know anything about this. I just found references and just show it. Right. This is probably survey of, relation between for debt result and etc. I don't know. And recent results, there are so many. But I'm not a player of Schrödinger's program. I'm just audience. So I'm just watching what's proved so often. Okay, let's go to the Nelson's program. I first introduced Schrödinger's equation, simple. It's if I understand correctly, I don't understand quantum mechanics, but if I understand correctly, Schrödinger's quantum mechanics is a quantum mechanics for one particle. Maybe something else, but I don't know. This denotes by V, potential energy, and the H Planck constant, and M is a mass of particle. Schrödinger's equation is simple. Schrödinger's equation is this. In the nonlinear case, B might depend on the absolute value of psi. Okay, and if initial, maybe I shouldn't. Maybe you know well, I guess, is if initial function is absolute value of initial function is probability density, then so is for n t. And Bourne interpretation is that the meaning of this guy is a probability density of a position of particle. Okay. Then Nelson's program is this. Okay, find the Fokker-Planck equation for this probability density. Well, if you put B by this, then this density satisfies this Fokker-Planck equation. And even if Schrödinger equation is nonlinear, this is true. Okay. So Nelson program is this. What's the equation of motion for quantum dynamics? By SDE, if you have since you have a Fokker-Planck equation, you have this program. Okay. And if this SD has a solution, then solution is called the Nelson process. Okay. Here I emphasize that P is a gradient of scalar function. Okay, I pointed out later about this. And well, when I was young, I learned the Nelson program by this book, and this is development of by another peoples. Here's a reference. First, they consider under this condition, which I call finite energy condition, they solved the existence of Nelson's program. First result was given by Karen in this paper. Approach was functional. I mean, he constructed semigroup and then showed that the existence of Nelson's program. Okay, this is by approach. This is by approach of stochastic analysis, and another approach. And in this paper, actually, by this time, by the recent terminology, I can say that we consider the multi-marginal Schrödinger's program and took continuum limit. Then we found we showed the existence of Nelson program, and indeed we considered, we didn't write down explicitly, but we considered the different kind of variation program which can be considered the continuum limit of Schrödinger's program, and I will discuss later. And the solution, and we found some kind of, in Nelson's program, drift vector B does not have to be a gradient of a scalar function, but in this construction, our drift vector V is always a gradient of H1 function. But drift vector of gradient field is unique in for the Fokker-Planck equation. Therefore, the process constructed in this paper is the same as Nelson's original problem. I mean, Nelson's process in his original paper. And here's the generalization of, this is also very difficult for me. I didn't understand by this. So, and well, in this paper, they, maybe I should, yeah. The difference of this guy and this paper is that in this paper, if I understand correctly, they also chose a optimal B. In this paper, for any drift vector B, they constructed as Nelson's program. And here's, in this paper, they constructed the Nelson program for jump type process. So I think this is the first result on Nelson's program for jump type process. Okay, maybe see, when I talk about somebody's else result, I might say something wrong. So please excuse me in advance. And next, I consider the generalized finite energy condition. In finite energy condition, R is equal to 2. We generalized it to more, less into the case with less integrability. Here, this function can be replaced by a superlinear function in my without any change of proof, which was pointed out by Professor Jin Feng, Kansas. I proved the existence of, under this condition, existence of Nelson process by the continuum limit of stochastic optimal transport. When I wrote this paper, I knew some duality theorem for stochastic optimal transport, therefore I could do that. And in this paper, we directly consider the continuum limit of stochastic optimal transport. And so proof is that we gave a direct proof for this for Nelson's program. Also consider the no, not now. Okay. And how about when? Yeah. So far, diffusion matrix is non-degenerate, uniformly non-degenerate. When it's degenerate, in this paper we consider the zero matrix case by the zero noise limit of Nelson process. And I didn't read the proof of this paper. This paper extremely generalized this. This is kind of, I think, probably remark, but this is a very nice result. But only the case when diffusion matrix is equal to 0. In this paper, they consider the degenerate diffusion matrix, but bounded, if I remember correctly. And this paper is very nice. He considered the degenerate case, the case of degenerate diffusion matrix, but L1 integral only only integral case. And this result, by this result, we extended our previous result recently. But I'm not sure if I have enough time. And this is a generalization of Trebison's result. And this is, in this paper, they consider the Nelson program for jump type process. So, okay. I'm sure I don't have time. Okay. Let's write down Nelson's program as a program of stochastic process. Okay. We suppose that A is a symmetric non-negative definite matrix, and B is a vector valued function and measurable, of course, and PT is a family of probability measures on RD. We write AB belongs to this set if this Fokker-Planck equation holds. Here I point out, emphasize that even if for each A, B is not unique in multidimensional case. Okay, so and A and B belongs to L1 function, L1. And if A and B belongs to L1 local, then we use this notation. Maybe I should write here local, but anyway. So Nelson program can be written in this way. When in PT, family of PT, such that this is not empty, and when AB, construct a semi-martingale such that this is a semi-martingale with quadratic variation process, this one. And marginal distribution of XT is equal to PT. And if this has a solution, they also say that the superposition principle holds. Sorry, superposition principle is missing here. Okay. And D. Trebison's result, if AB belongs to this set, then Nelson program has a solution. And its generalization is this. Instead of integrability of A and B, suppose this is true, then Nelson program has a solution. And this result has a nice application to stochastic optimal transport with non-convex cost function in one-dimensional case. But I'm sure I don't have time to talk about it. Yeah, finally, so, okay, let's talk about stochastic optimal transport. Well, it's complicated, but anyway, we consider semi-martingale actually. And quadratic variation process of martingale part is fixed, but bounded variation part is not fixed. Okay. And we consider the case when L is a cost function, but convex in the last component. And stochastic optimal transportation program, we consider this. We first fix initial and terminal distribution and take infimum of this guy, where beta is a derivative of bounded variation part of xt. Next, we fix marginal distribution for all t and take infimum of this guy. If this infimum is empty, we set the infimum for infinity. Okay, this is stochastic optimal transportation program. And I introduced two more programs. One is this. We consider the same problem for over the solution of Fokker-Planck equation, okay, which satisfies these constraints. In this case, since marginal is fixed here, this pt is fixed, but b is not fixed. Here, b is not fixed, and this measure is not fixed, but satisfy this constraint. Okay. Another problem is the next stage. First, I introduce notation for the measure mu on this product space. Mu1 by mu1, we denote the first marginal, mu2 the second marginal. Okay. And we consider measure mu dt dx du. That it's a distribution of and probability. And first marginal is a uniform distribution Z1. And this is integration, disintegration, and this new t. The first marginal of this new t is has a weakly continuous version, and this is true. This kind of approach to consider Hamilton-Jacob equation is not my original idea. It's I learned this idea from Professor Diego Gomez lecture in Tokyo, also Professor H. Evans lecture. But anyway, idea is that instead of distribution of xt, we consider distribution of xt and beta t, drift vector. So it's the idea, and it originally comes from Mazur theory, which is a variation problem of invariant measure of dynamical systems. But anyway, and then we consider the same program. He has pointed this. In here, this integration is linear in nu, right? So we linearize the program in each case. And if P belongs to this set, then as nu, we consider this. For semi-martingale, nu, this measure corresponds to nu. And the set over which we take infimum is bigger and bigger as the number becomes bigger. So this inequality always holds. But the superposition principle implies that this becomes equality and makes problem much easier, right? And here's another point. See, this is in the second program in each of three variation programs. Second program is always this is a family of probability measure, but we identify this family of probability measure with this measure. It's a very nice point to consider second programs. Okay. And yeah, if cost function is convex in U, then equality holds. Okay. No way. Yes. Equality holds. And L is superlinear in U, uniformly in T and X, then minimize, you have minimizer is of this can be written in this manner. But well, this is not that much important, so I skip. Okay, next. Okay. I explained I described the theorem. Or maybe I should, yeah. Here, important assumption is this superlinearity of L function L and the convexity of this. Some other regularity result. Okay, this is regularity result assumption. Let's take by this we define the Legendre transform L with respect to U. Then under these assumptions, first program has this theorem, this reality then where phi denotes a minimal bounded continuous viscosity solution to this HJB equation. Actually, this can be written as an infimum of some mean value, I mean, stochastic control representation. And we assume the regularity of Aij and L. Then we have, sorry. Yeah. Then this minimum bounded continuous viscosity solution becomes a classical solution. Okay. Yeah. Right. I skip. And then solution or classical solution, we have this equation is in particular optimal drift vector beta is a function of t and xt. And for the second program, we also have the duality theorem. Since we identified family of PT with dtpt, right? Here, but the HJB equation is different from last one. It's here. Oh, sorry. So basically, yeah. And right. And this is a, oops, sorry. It doesn't work. This phi denotes a minimum bounded continuous viscosity solution. Yeah. And if HJB equation has a classical solution, optimal drift can be written in this way. It's a function of t and xt. So yeah, in Schrödinger's problem, I gave sufficient conditions for the finiteness of Schrödinger's program. In this general setting, we have this. For example, if initial and terminal distribution has a density and satisfies this integrability condition, then there exists BTX such that this has a weak solution. Oh, sorry. Okay, this SD has a weak solution. Since this has a weak solution, you can consider a variation problem when L is of order U to the R, right? At least there exists one XT such that this is last line is true. Okay. So this gives a sufficient condition for the finiteness of B. Yeah, here's a reference. Okay, maybe I cannot complete. The first result was with Professor Mr. Churen in Paris, and when she kindly gave me the opportunity to visit Paris for a month. In that case, in this paper, we only considered the A, the diffusion matrix is identity, and we gave a duality theorem B by classical solution. And we use a lower sum continuity, convexity of B in P1 by Cameron-Martin formula, and lower sum continuity by the titles of Martingale. And this paper, we consider Zeron's limit of duality theorem. And then, yeah, only in this case. And in this paper, we generalized it to the case when A is uniformly non-degenerate, but we consider duality theorem for each variation program, right, separately. And but the Hamilton-Jacob equation was considered in the viscous solution and the classical solution. But the idea was basically the same. We formulated the program by viscosity solution because it's an international conference for viscosity solution. Okay. And in this paper, they consider the same problem, but slightly different setting. Here, A can be degenerate, but in their setting, this set is closed convex. So it's not always true. So if A is identity, that's fine. This is true. So the setting is different. But the point is this: they didn't consider the distribution Px, but also Px and bounded variation part of X. But the tightness for semantic is ideal to use tightness for semantic is the same. And in this paper, thanks to superposition principle, oh, I should stop now. A can be degenerate, and this is true. And the approach is so different. I mean, superposition principle plays a crucial role to prove that convexity and lower semi-continuity of this guy in P1. This is a new approach. But the difficult part is from somebody from Tripson's paper, not me. A good thing is, since we linearize program by the last guy, we don't have to use this assumption. This assumption was also supposed in Tantuzi's papers because they consider tightness of semantic. This assumption is often used to prove the lower semi-continuity of action integral. So, and this is a paper that gives sufficient condition for this. And the idea of the proof is this. Let's set this for any p. Okay, this is n. Probability measure p. I set a sublevel set of this integral. Then, under assumption, for any compact set k, this set is compact in this set. Then you can prove that lower semi-continuity of this guy and this guy. Convexity is much simpler. Okay. Here's a application of another result, but I think I should stop here. Thank you for your attention. Sorry, I couldn't speak everything. Okay, that's it. Thank you.
So if anyone has questions online, please you can just unmute yourself and ask your question. And if someone in Lisbon has a question, I can pass on the microphone. That's the easiest way to do that. So maybe, Jean-Claude, I will give you the microphone if you want to pass it to someone else, just check online.
I have a very naive and a non-technical question. Is it audible, what I'm saying?
I think so. Yeah, you should be clear by everyone. Yeah, go ahead.
So if we start from the classical Schrödinger problem, I'm wondering what I can tell my analysis colleagues who are very familiar with the concept of entropy and so forth. And I wonder what I can tell if I introduce the Schrödinger problem to my analysis colleagues, what I can tell them in order to impress them that stochastics is actually needed to solve the problem. What would be your answer to that, given all your expertise and all these versions and methods to say that you have solutions for the stochastic part of the variational problems? How much can you use this to impress the colleagues from the analysis laboratory?
Okay.
Does stochasticity help to understand if you are just an analyst?
Yeah, let's consider Nelson's problem case. Okay, it's a continuum limit of Schrödinger's problem. If Schrödinger's equation is nonlinear, for example, when you consider the laser beam, then it's a nonlinear Schrödinger equation and explode within finite time. To study the asymptotics. I mean, for example, for some time t, solution of nonlinear Schrödinger equation explode. But absolute, density, square of absolute value of Schrödinger's of the solution to Schrödinger equation is a probability density. Probability density might converge to some irregular, singular probability measures. And actually, I was asked by a PD guy if I can do some contribution. And Nelson process has some contribution to this asymptotics of this, density when the solution to Schrödinger equation explode. But the difficulty is this, and if you have some if you have estimate of L1 norm of B, or maybe I should, sorry. Oh, okay, let me pass. Yeah. Oh. Yeah. So this is probability density, right? And even in the case of nonlinear Schrödinger equation, that is this V depends on psi. We have this same program, and the L1 norm of B plays a very crucial role in the case of nonlinear Schrödinger equation, for which the solution explodes within finite time. See, interest is asymptotics of this density. This density times dx, distribution of a particle. Even if solution explode, distribution might converge to some singular measure. It's known. And to consider this kind of program, L1 the boundedness of L1 norm of this drift vector is very important. Then and PD guy asked me if I can prove it. I proved something, but it was not enough. So I think it might be a good application to consider this kind of nonlinear Schrödinger equation. Distribution of the laser beam program by this Nelson's program. Also, by approximation, maybe marginal Schrödinger program might be useful near the explosion time. I don't know. Yeah. I hope I explained something.
Okay, I have a question. Is your theory of stochastic optimal control poses some, some relations with Fleming's theory of controlled Markovian process?
Mm-hmm. I was a student of his.
Yes. So do you have some relations? Your theory of stochastic optimal control and Fleming's controlled Markovian process.
Okay, let's see.
Yeah,
I think I can.
Are they the same? Or?
Wait a minute. So, okay. For example, finite time horizon control program can be written by this stochastic optimal transportation program. It's very difficult to explain, but I don't know. So, stochastic optimal transport is kind of a fundamental solution for for finite time horizon stochastic control program. I'm sorry, I don't know what to say. Yeah. So I'm sorry, I don't have explanation. So for example, if terminal function is no way. Nah, what I can say is that maybe I should write. Maybe we should break it.
So thank you, Professor Mikami. And just for everyone, so we in Lisbon are lucky enough to have a coffee break, and we will reconvene in about 20 minutes time. So that would be 11:50 European time. And for the rest of you, I'll leave you the computation. So thank you all, and see you very soon.